Why Buildings Stand Up, Chapter 11, Form Resistant Structures. So the authors start out talking in this chapter about kind of the evolution of challenging structures, and specifically they talk about assembly halls. And assembly is a word that's used in the building code and the fire code to mean a place where a large number of people assemble. This is structurally challenging because you're trying to create an open space with no intermediate supports. You know, you can imagine a basketball court with a column running up through the center to support the roof would be dysfunctional, and so assembly occupancies tend to be structurally challenging. Now, in antiquity, almost all of our building materials were strong in compression and weak in tension. So again, they would display that property we call anisotropy, where they are anisotropic. They are strong in one direction and weak in another. And the only way to make materials that are anisotropic span long distances is to develop a curved shape. So if you think about long spans of antiquity, they were always arches or domes. Even wood trusses generally fall under this limitation, even though we know that wood is not nearly as isotropic, or excuse me, as anisotropic as stone. You think about if you wanted a long span like a grocery store or a bowling alley, a common truss was the bowstring truss. What started to change that was the development of building materials that were more isotropic. And kind of the classic examples are structural steel. That's highly isotropic, very strong in tension, very strong in compression, and reinforced concrete, which we've discussed a lot in this course. And remember that reinforced concrete is a composite between concrete, which is the compressive member of the composite, and reinforcing rebar or tensioning tendons, which are the tensile parts of the structure. So those came together, and with steel structures or with reinforced concrete structures, we're able to span great distances without taking on that arched shape. Now, figure 11.1 is a good example of that. This is a reinforced concrete grid, or it could very well be of steel, but I would say that most commonly you'd see this type of grid out of concrete. And there are a couple of characteristics that are important in this grid. One is that if you think about the relative width and length proportions of this, you'll notice that they are similar. Right? That this width here is maybe not equal to, but certainly within a factor of some percentage equivalent to the length. And if you think about why that is, if we think about applying the load right here, we want the load to be shared equivalently between this beam running kind of front to back and this beam running side to side. And you'll recall when we read about Hooke's law, Hooke had this saying in Latin, but converted to English it was, as goes the stress, so goes the strain, or as goes the strain, so goes the stress. Well, if you think about when we talked about materials in this class, if we were to draw this graph of kind of material, stress versus strain curve behavior of material, this was strain on the horizontal axis. It represented kind of the extent to which the material was being stretched or compressed or bent. It was changing its shape in a way it didn't want to. And this was stress. This was basically proportional to the force developed in the material. And remember that we have this kind of these two regions on this graph. There's the elastic region over on the left side, and there's the plastic region over on the right side. And we always want building materials to be operating in this elastic region. And in this elastic region, what Hooke's law says is that this is a straight line. Basically, in this region, Hooke says that stress is proportionate to strain. And because that's the case, what we want, if we want both of these two beams to develop the same amount of force, they have to feel the same amount of deflection. Well, certainly they have moved down the same amount at the point of this arrow here, but they would find that they would have different deflections if they had different lengths. Essentially, if you made this left to right beam twice as long, it would only develop a quarter the stress from the deflection, and so it would not carry its share of the load. So one of the characteristics of this type of grid is that they have to be approximately equal left to right and front to back. Of course, if this is a concrete grid, we're going to get our tensile strength. We're going to develop our tensile strength by putting rebar in the bottoms of those structural members, which is what you would see as this was cast. This is a recreation of a grid structure from antiquity. Obviously, anything that's that old that was made of wood is long since gone. But you can see that it follows the same principle, that the relative distances, the relative lengths of the spans of the side of the structure are about equal, which is central in all grid-type floor structures. Now, this is a really kind of innovative way that some structural engineers got around that need for length and width to have some parity, to be nearly equal to each other. This is called a skew grid, and if you'll notice, essentially all of the members of this grid, once you get away from the corners, are exactly the same length, and it doesn't matter if they run in this direction or they run in this direction. So effectively what we've done is we've got a structure now that's got a large length and a short width, but by skewing the grid, we're able to average those two together so that instead of having some beams that are very long and flexible and don't carry much of the weight, and some beams that are very short and stout and do carry a lot of the weight, by skewing them, we're able to make them all the same length and, as a result, kind of all equally rigid. So you're going to see this in a number of the buildings in this chapter. Again, common material for this would be reinforced concrete. Reinforced concrete works well because we want to make these joints rigid so that basically any movement of the joint causes twisting in all of the surrounding components. And we've talked, I think, in other chapters about this idea that these will develop this kind of inflection point behavior where each surrounding component gets twisted into kind of an S shape. So reinforced concrete works well for that. It certainly could be of welded steel construction, although that would be expensive. And occasionally you will see these constructed of wood, commonly called a lamella type roof if it's constructed of wood. If the concept of the grid is taken to its extreme, where we have kind of an infinite number of infinitely close gridded members, you develop a slab, which is what you see here. And this is what we might call a monolithic slab. Just mean it's poured out of one solid piece of concrete on site. So the way that this was constructed is that wood formwork was placed below the slab. And in this case, they're using these clay tiles basically to take up volume in the slab without adding weight. Remember that, really what matters for the strength of this slab is this relative height, right? How far we can separate the material that's under compression from the material that's under tension. And for the moment, I'm going to say that the top's under compression, the bottom's under tension, and recall that halfway in between we have this neutral axis, which is neither under tension nor compression. So the real strength of this floor structure is near the top of the, actually the floor above and the ceiling of the floor below. Now you'll notice that this has rebar placed top and bottom, which may seem a little counterintuitive because you would expect that the top of the floor slab would be in compression just by simple beam action, right? If you think about a simple beam spanning two supports, it takes on this kind of curved shape. Oops. And the top of this beam is in compression, and the bottom of this beam is in tension. But if you think about if this beam were to continue on the other side of this support, well, then it's going to take on this kind of S shape. And so if I redraw the shape of this thing with the supports, it actually takes on a shape that looks a bit like this. Well, on these convex side up parts of the curve, there is tension, and on the concave side down, there is compression. They're getting shorter. And then in the center, on the concave up part, there is compression, and on the concave down part, or convex down part, there is tension. So you can see that it depends on where the supports are and where the floor is loaded, whether the tension is in the top of the floor or in the bottom of the floor. To be ready for all possible scenarios, the floor is constructed with reinforcing bar, both top and bottom. And this is really, pretty economical to just put rebar on both sides of it. What you end up with is a very, very robust floor structure. It's quite stalwart against fire, very difficult to penetrate this with fire, good soundproofing, and it's a floor that gives the users of the building an impression of a very solid building. This floor doesn't creak or groan or shake at all because it's massive and also quite rigid structurally. This slide describes developable and non-developable surfaces. And the way to think about a developable surface is if you could take a sheet of paper and fold it into that shape, it is a developable surface. So you can see here that that this kind of arch shape is just simply a bend in this piece of paper. On the other hand, this dome shape, there's no way to develop a dome shape from a flat sheet. In fact, if you were going to construct a dome like out of sheet metal, you would develop a pattern that looked something like this, where you'd have to cut slits out so that these edges could move together, because the circumference around the base of this dome is quite a bit less than the circumference of a circle with a radius equivalent to the distance from the surface of the dome to its base. And so you have to be able to remove some materials. If you wanted to see a practical example of a dome that was constructed in this method, you could go to the Alliant Energy Center, and out in back of the Alliant Energy Center is a globe that was constructed of sheet metal, and you can actually see in the sheet metal this pattern where the tin benders had to cut a very specific pattern to get the dome shape out of it. It's actually very interesting work. The things that can be made out of sheet metal, if a person understands geometry, are quite impressive. One of the characteristics, in addition to the fact that you can't make the dome from a flat sheet, is that you can't push this dome into a flat sheet without compressing the material in the center of the dome. And a dome is kind of like a beam in the sense that there's this circumferential band here where there is neither tension nor compression, and I'm just going to call it neutral for our purposes here. Above this band, the dome is under compression. Below this band, the dome is under tension. So in domes of antiquity, one of the things that we've seen over the years is that these domes develop these tensile cracks at the base, and then they have to do some type of attempt at a repair, like belt it with a large chain or something of that type. Above, they're in compression. Now, domes of antiquity were made of materials that were strong in compression, and so we don't tend to see, for instance, the tops of those domes failing. They're quite robust to that. But a place where you might see this is if you think about the shape of like your car door. Your car door gets its strength from the fact that the sheet metal has a certain bit of geometry to it. It's been bent into a non-developable surface in its manufacture. There's no piece of metal on the outside of that car anymore that's any thicker than maybe a cookie tin. But all of the strength is in the geometry. And this is why when we flap a roof, we take a pike pole to create a crease. We're trying to take the geometry out of the metal. Well, you can imagine that if your car door has this nice non-developable curve and someone, puts their foot in it or something and pushes it in, what's got to happen is kind of near the vertex of the curve, that metal is under compression, but sheet metal doesn't handle compression very well, and you get wrinkles in the metal. And so what you'll have is that, once they've dented your door, if the metal has become wrinkled, there's no way to repair that really. The other possibility is that, just kind of depending on how the dent proceeds, is you may stretch the metal that is under tension. And there is actually a strategy for that. There's a tool called a metal shrinking hammer, where if a dent has gone into a piece of sheet metal and it has tensed the metal until the point that it is plastically deformed, a skilled collision repair tech can actually shrink that stretched region back to its original size with some significant hammer work. Of course, nothing in the collision shop is less than $2,000, so we tend not to see a lot of that type of work anymore today. It's just cheaper to replace parts. But the moral of the story is when we're cutting on modern cars, this principle of non-developable surfaces is just as applicable as it is in building construction.